Okay, notes for 4-7 on the law of sines and law of cosines. So in this section, we're going to solve triangles that are not right triangles. They are what we call oblique. They have no right angles in them. So we're going to use some trig still so that we can find the values of the sides and the values of the angles. And we're also going to see some formulas where we have the area that we can find for these oblique triangles. So in chapters 4 and 5, we spent lots of time working with right triangles and all of their characteristics. But now we're going to look at ways to find unknown values for triangles that do not have right angles. So we're still going to use law of sines and cosines, but these will be oblique. Okay, so first we're going to look at the law of cosines. So for the law of cosines, we're going to use this when we are given the measure of all three sides, in other words, side, 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 or the measure of two sides and the included angle, so which would be side, angle, side. So here is the law of cosines, which looks like three equations, but it's really not. It's really just a pattern. So if you look at triangle ABC over here, triangles A, B, and C, and they have corresponding opposite sides, A, B, and C, it says the following. So the first equation we have is A squared equals B squared plus C squared minus 2BC times the cosine of A. So what this is really saying is that if we are looking to find angle A, or if angle A is the focus, that's the one that's included in the formula, then it's the side opposite of angle A squared that is equal to the other two sides squared, B and C squared, minus 2 times the side B and C times the cosine of A. If you look at the second equation, B squared, so now this includes angle B. So if we look at angle B now as the angle, the equation would be that B squared, the side B squared, is equal to the other two sides added and squared, minus 2 times A times C times the cosine of that angle. So it's the same pattern once again. And then if we were looking for angle C, or if C was the focus angle here, we would have side C equal to the sum of the other two sides squared minus 2 times A times B times the cosine of C. So really, it's not a matter of the A's, B's, and C's and memorizing that. It's just the pattern that we need to see. So let's look at example 1. The first thing we have is a hockey player attempting a shot. He's 20 feet from the left post of the goal, 24 feet from the right post of the goal as shown. So everything's labeled for us. Now a regulation hockey goal, they said, is 6 feet wide. What is the player's shot angle to the nearest degree? So we're trying to find this small angle in here. So if we want the angle, what we have given is three sides. Side, 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 20, 24, and 6. So our angle that we want is angle A. So we're going to say that A squared, the side opposite, is equal to B squared plus C squared minus 2 times B times C times the cosine of angle A. So if we plug that in, we would have 6 squared equal to 20 squared plus 24 squared, oops, that's a degree mark, sorry, plus 24 squared minus 2 times 20 times 24 times the cosine of angle A, and that's what we're solving for. So we can simplify all of these squares and combine some of these like terms. There's really two ways to do this, but one thing you might see in other books is you may see it all solved for the cosine of A. So what we would have would be 6 squared. We'd subtract off the 20 squared, subtract the 24 squared, and then we would divide by the negative 2 times 20 times 24. And that would be the cosine of A. And then, of course, angle A would be the cosine inverse of all of that. So we would take the cosine inverse. So making sure that your calculator is in degree mode, you could do the cosine inverse of this whole thing, or you could do all of this, get that decimal value, and take the cosine inverse of your answer. Either way you choose to do it, you should get angle measure A, to be 12 degrees. And that would be the shot angle. Okay. So, the next example, we're going to solve for all three angles and all three sides. So we're going to round the side lengths to the nearest tenth and the angle measures to the nearest degree, and that's typically what we're going to do. So if we look at what we have, the information given is a side, an angle, and a side. So we have the 8, the 65, and the 5, two sides and the included angle. So with this, we can use the law of cosines. So the first thing what we're going to find is side C, because I have angle C. So I would say that C squared would be equal to the other two sides squared, 8 squared plus 5 squared, minus 2 times the other sides, 8 times 5, times the cosine of 65 degrees. Making sure your calculator is in degree mode, you're going to enter that calculation in, and you may want to, just to avoid any errors, simplify this down a little bit. 64 and 25 minus 80 times the cosine of 65, and then this would give you 89 minus 80 times the cosine of 65. A little less likely to make a careless mistake when you're only plugging that much in. So when you plug that in and you solve for C, so we take the square root of that, you're going to get 7.4 as our C value. So C is 7.4. Now what we can do is go on and find the other angle. So now I could find, let me see, what did I do? I found cosine of, let's find A. Change colors here. So now let's find angle A. So what we could do was we could say that if we're after angle A, we could say 5 squared is equal to 8 squared plus 7.4 squared minus 2 times 8 times 7.4 times the cosine of angle A. So now if we're going to solve for angle A, hopefully this isn't going to be too big of a jump. This is just some algebra here, lots of algebra. We've got the cos inverse of, we would take 5 squared minus 8 squared minus 7.4 squared all over negative 2 times 8 times 7.4, and that would equal angle A. So it's taking everything off the left and putting it on the right over there, and then taking the cos inverse of it. Lots of algebra. Okay, so when we do this, angle A, we get to be 38 degrees. So now that we know A is 38 degrees, we can go ahead and we can find the other angle B, which is just going to be 180 degrees minus 65 degrees plus the 38 degrees, which is going to be 77 degrees. So we've solved the triangle. We have side C of 7.4. We have angle A of 38 degrees and angle B 77 degrees. So these are two ways that we've used the law of cosines, one where we're given all three sides and one where we started out with side, angle, side. Okay, before we do law of sines, we're going to look at finding areas of oblique triangles. So we know that with a right triangle, the area is half the base times the height, but that's when you have a base and a height that are perpendicular. So if you don't have a right triangle, that's pretty difficult. So there are two different formulas that we're going to use for finding the area. The first one is Heron's formula, and this is used when we are given side, side, side. So taking a look at Heron's formula in this first gray box, if we have all three sides, then we can express the area of the triangle like this. It is the square root of some number s times that number minus side A times that number minus side B times that number minus side C. And there are a few parentheses missing under here, so sorry about that typo. Now what is S? It is half the sum of the sides. It's not the average of the sides, but you add the sides up and you take half of it. And that is your S value. So as we look at this, we have the first example where we have triangle ABC, and we want to find that area to the nearest tenth. So having side, 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 the first thing I'm going to do is find that value S. So S is going to be 1/2 the sum of 51 plus 38 plus 45. And that's half of 134, which is going to be 67. So 67 is the magic number. So now the area is going to be the square root of 67 times, and then we just take that number and subtract each side. 67 times 51, or minus 51, sorry. 67 minus 38, 67 minus 45, and then all of that under the radical, and I don't know in the particular order, is going to be 67 times 16 times, let's see, 29 and 22. And when we take the square root of that, the area will be 827 square inches. Okay. So that's finding the area of an oblique triangle when we have the three sides. Now we're going to look at the other area formula that we have. And this one is just, there's no specific name for it. It's just when we are given side, angle, side, side, angle, side. Okay. So again, it looks like three formulas or three algorithms, but it's really not. So the area of the given triangle is half the product of the lengths of the two sides that are given and the sine of their included angle. So if you're given A and B and C, that side angle side, it would be 1/2 of B times C times the sine of A. If you were given angle B and sides A and C, there's side angle side again. It would be 1/2 of A times C times the sine of angle B, and vice versa with C. So it's half the product of the two sides and the sine of that angle. So let's look at example 6, letter B, and we'll apply this one. So we have side angle side, 10 centimeters, 7 centimeters, and 108 degrees. So we're going to use this formula. So area is equal to 1/2 of 10 times 7 times the sine of 108 degrees, which is really going to be 35 times the sine of 108 degrees. And the area will be 494, when we round, miles. Or, sorry, how about, no. How about 33.3? I'm looking at the wrong problem. How about 33.3 centimeters squared? Okay, and those are a couple of different scenarios where we can find the area of an oblique triangle. All right, now we're going to use the law of sines. So the law of sines is something you can use when you're given different information. So with the law of cosines, you need side, angle, side, or you need side, side, side. But with the law of sines, to solve an oblique triangle, you're given the measure of two angles and a non-included side. So this is when we are given angle, angle, side, or two angles and the included side, angle, side, angle, or two sides and a non-included angle, which is side-side angle. Now this very last one, that will lead us to a possible ambiguous case, which we'll talk about in the second half of this lesson. Okay, so here's what the law of sine says. It's really just proportions. If you have a triangle with side lengths ABC and the angles A, B, and C, then we have sine A over side A equals sine B over side B, and sine of C over side C. So we're going to solve triangle number 3, in example 3, triangle ABC, rounding side lengths to the nearest tenth and angle measures to the nearest degree. So I have angle, angle, side. So what I can do is I can say that the sine of 103 degrees over its opposite side of 20 is equal to the sine of 35 degrees over side A. So in doing that, I can get that A times the sine of 103 degrees is equal to 20 times the sine of 35. Then I would divide by the sine of 103, and A would be 20 times the sine of 35 over the sine of 103. And when I calculate that, I get A to be 11.8 as that other side. Okay, so then very easily the way that we can get angle C is simply just to take 180 degrees minus the sum of 35 and 103. So that's going to give us 42 degrees for angle C. And we can write that in there. Erase that. Okay, and then, so we have angle C, we have side A, and we need side C now. So to find side C, we can take the sine of 42 degrees over side C, and that's equal to the sine of 103 degrees over 20. So we know that C, side C, would be 20 times the sine of 42 degrees all over the sine of 103 degrees. And that's going to give us a side length of 13.7. So there we have the two sides and the angle, and we've solved for our triangle. Okay, the next example is an application, and sometimes the toughest part of these is to actually picture what's going on and draw it. So you really have to work your way through these and just kind of focus on what's going on. An Earth orbiting satellite is passing between Oak Ridge Laboratory in Tennessee and the Langley Research Center in Virginia. Now they are 446 miles apart. So I'm going to draw this Oak Ridge Laboratory location and the Langley Research Center, which the distance there is 446. Okay, so 446 is my distance, and then there's a satellite up here. And so it says the angles of elevation to the satellite from the Oak Ridge and Langley facilities are 58 and 72 degrees respectively. So in that order, it's 58 degrees from Oak Ridge and 72 degrees from Langley. So they want to know how far is the satellite from each station. So I need to find, let's call this X and Y. Well, when I know all three sides of the triangle, or all two of those angles of the triangle, I can find the third angle by just simply doing some math on that. So I can say that 180 minus 58 plus 72 is going to give me an angle of 50 degrees, which is important because the only side I have is the 446. So now I can use my law of sines. So I have the sine of 50 degrees over 446 is equal to, let's do x, the sine of 72 degrees over x. So x is equal to 446 times the sine of 72 degrees, and then that'll be divided by the sine of 50. When we do that and we figure that out, we get 554 miles. Then we're going to take a look at y and find the other distance. So we need the sine of 58 over y equal to the sine of 50 over 446. So y is going to equal 446 times the sine of 58 over the sine of 50 degrees. And that's going to give me a distance of 493 miles. Okay, so this completes the law of cosines and the law of sines. And now we're going to go into the ambiguous case for the law of sines. So the last part here. So in geometry, we never did use SSA, side-side angle, to prove similarity, but we can use the law of sines to solve a triangle. The reason that we didn't before was when we were given that, it would be possible to have either one, two, or no triangles at all, and that's kind of tricky. So we're going to talk about using this to solve a triangle now. So there's different cases that can occur, and the law of sines, the ambiguous case, let's take a look at those three scenarios. So in a triangle where ABC are given, the following describes how many triangles are possible. For the acute case where we have the sine of A equaling h over b, or the height, this is what we're going to use a lot, equaling b times the sine of A. So, so what we have is, let's first of all look at the acute angles. If you are given two sides and then an obtuse angle, if you have A being less than B, then you would have no solution at all. If you have A being greater than B, then you would have one solution. So on my Canvas page, there's a video about whether or not a triangle even exists. It's like 4.5 minutes long, and it's really, really good. They talk about when you're given an obtuse angle, so I would strongly suggest that you take a look at that video. Okay, now also when A is acute, they talk about this a little bit as well. I want to jump around here just a little bit. So when A is less than B, this first one. So if A is less than B, but then we figure the height, and it's also less than the height, there would be no solution. It's not going to be long enough to touch that third side. If we find the area and it is equal to h, or if we find the area, if we find A and A is equal to the height, that means we have one solution. We actually have a right triangle. If we have A being longer than B, then we can only have one solution. And here is the ambiguous case. When we have A being longer than the height, but shorter than the other side B, we can actually think of that side A being on a pendulum and swinging and giving us two different triangles. So this is where we want A to be in the middle between the height and the other side given. So The height is the smallest, then A, and then B, and we'll have two triangles. So again, the ambiguous case is when you have side, side, angle, okay? So to solve the ambiguous case triangle, first you want to determine the number of solutions that you have. If the triangle has one or two solutions, we're going to use the law of sines. So example 5, letter A, we want to solve this. So I have side A is 15, side C is 12, and angle A is 94. So I'm going to sketch this. Now this is an obtuse angle, so there's two things that can happen. There's A at 94. Now I'm going to draw this completed, whether it can be or not. So A is 94, side A is 15, and side C is 12. Now I always write my triangles this way, so that I have the angle, the opposite side, and then I have that other side always over here to the left of the angle. It's just the way I always do it so that I can always keep my perspective the same when I'm doing these. So when I look at this, A is longer than B. 15 is greater than 12. So what that means is I'm going to have one solution. So if I have one solution, we're going to go ahead and use the law of sines to find the others. We need to find side B, and we need to find angle C and angle B. So I'm going to take the sine of 94 degrees over 15, and that's going to equal the sine of angle C over 12. So to find angle C, I am going to cross multiply. So I have 12 times the sine of 94 equal to 15 times the sine of C, and divide by 15. So C, angle C, will be the sine inverse of 12 times the sine of 94 degrees over 15. And in this case, angle C is going to be 53 degrees. Okay, so I know that C is 53 degrees, so now I can continue to find some other pieces. So now I can find angle B, because I know angle B will be 180 minus 53 plus 94, and that's going to give me an angle measure of 33 degrees. So there's angle B. The last thing I need to find is side C. So I'm going to take the sine of, side B. So I'm going to take the sine of 33 degrees over B, and that's going to be equal to, you can pick one or the other. I'm going to use the sine of 94 over the opposite side, 15. So when I do the math on this, B is going to be 15 times the sine of 33 over the sine of 94. And we have side B equaling 8.2. All right, so that solves that triangle with one solution. Then we're going to look at the next one. And so I have angle A at 61, side A at 9, and side B at 11. So there's A, B, and C. So I see that 9 is less than 11. So I know that maybe I have two solutions, or maybe I have no solution, or one solution. I'm not sure. So I'm going to find the height of this and see where 9 measures up to the height. So to find the height, I know that that's going to be the sine. I can use some right triangle trig here. The sine of 61 degrees would be the height over 11. So 11 times the sine of 61 degrees is equal to h. And in this case, the value is 9.6. So with it being 9.6, the height is actually longer than the other side, which means that it's not going to go all the way down and touch, so there's no solution. And we just kind of move on from there. All right, so we have a couple more. Let's look at example C. So in example C, we have an angle of, and actually, there's not a lot of room to do these. I'm going to actually draw this triangle up here. We have an angle of 43 degrees at A. We have side A at 25 and side B at 28. So there's my triangle ABC. So I know that 25 is less than 28. So I have some options. I could have no triangle, I could have two triangles, or I could have one triangle. So what we need to do is test the height. I'm going to draw this perpendicular height, and I'm going to see what that is. So the sine of 43 equals h over 28. And so then 28 times the sine of 43 equals h. So when I do this, I only get about 19. So what this means is this is the ambiguous case. Okay. So with this, now I'm going to just, triangle number 1 will be this triangle. This means, let me draw this out. This means I'm going to be able to take this 25 and actually swing it in here for another triangle, an obtuse triangle. So I'm going to have the original, and then I'm going to have another one that looks like this. There's my A, my C, and my B. I know that A is still 43, this is still 28, and this is still 25, but that's going to be triangle number 2. So as I solve this, I'm going to actually make a little chart. I have triangle 1 to solve for, and I have triangle 2 to solve for. Both of them need an angle B, an angle C, and a side C. And that's what I need to get to solve this this problem. So what we have is we look at the top one, the original, and we're going to go for angle B. So we're going to take the sine of 43 over 25 is equal to the sine of B over 28. So when we cross multiply and we solve this, we get the sine inverse of, and then we have 28 times the sine of 43 degrees all over 25, and that's going to be our angle B. And as I look at that, I'm going to get 50 degrees. So this is our first measurement there. Then to find angle C, all I need to do is some simple geometry. 180 minus the sum of 43 and 50. So that's 180 minus 93. So we have a measurement of 87 degrees. So then the last thing we have to find is side C. So now that we know we have 87 degrees at the top, we can do the sine of 87, which is angle C, over side C, And then we can still do the sine of 43 degrees over 25. And when we solve for C, we're going to get 25 times the sine of 87 over the sine of 43. And side C is going to be 36.6. So 36.6 is that side. Okay. So now, when we have this first triangle taken care of, we need to do the second triangle. So I'm going to take this second triangle, and I actually want to, if I can move it all the way down here where we have some more room, and I'm going to work with this one. So now, here's what we need to remember. This was here. What we originally had was the other 25 was out here. And we found this angle to be 50. But then when we swing this in, this angle is also 50. So to find this obtuse angle, 180 minus 50 gives me a 130 degree angle. So to find angle B for this triangle number 2, I'm going to take 180 and subtract 43 plus 130. And that's going to give me 7 degrees for angle. Wait, that was angle C I was finding. Yeah, B is 130. This should have been angle C, I'm sorry. So C is 7 degrees. B was 130. So there we have B and C, and now we need to find the new side C for this other one right here. So I can take the sine of 7 degrees over C, and that is equal to, I can do the sine of 43 degrees over 25, and when I solve for that, C is going to be 4.5. And that's the last piece. So as I fill in this last piece, angle C was 7, angle B was 130 degrees, and side C was 4.5. So this is your ambiguous case where you have two different triangles that work for the information that you were given. Okay, we have one last one to do. It's another one with the ambiguous case. So here we go. Let's draw angle A, which is 26. We have side A, which is 5, and side B, which is 9. So again, we have side A is less than side B. So we possibly have 2, 1, or none. So we need to check the height. So as we check the height right here, hopefully now, and after you practice this a little bit, you're going to learn that the height is the side times the sine of the angle given. And as I look at this, the height is 3.9. So this means the ambiguous case, I have 2 triangles to find. So I'm going to go ahead and make my chart. There's triangle 1, triangle 2. For both of them, I need to find an angle B, an angle C, and a side C. Okay. So, as I look at these now, I'm going to just look at this first triangle before I rotate that side of 5 in and swing it the other way. So I'm going to take the sine of 26 degrees over 5 equal to the sine of B over 9. So 9 times the sine of 26 degrees is equal to 5 times the sine of B. And hopefully now we're going to see that the sine inverse of B will be 9 times the sine of 26 divided by 5. and that's going to be angle B, and in this case we find it to be 52 degrees. Please make sure that you're pausing this video and you are finding these values yourself. Some of the toughest parts of this is truly plugging it into the calculator. There are so many mistakes made doing that, so just be very, very careful and make sure that you are able to get these values in the calculator. Okay, then we're going to find angle C here with some simple geometry. 180 degrees minus the 26 plus 52 is going to give me an angle C of 87 degrees. So we have angle B at 52, angle C at 87, and now we're going to go for side C. So I'm going to do the sine of 87 degrees over C, and then I'm going to also still use the sine of 26 over 5. So side C will be 5 times the sine of 87 over the sine of 26. And we will have a value of 11.2. Now wait a second. This angle C was so wrong. I took it off of my notes from the wrong chart. So that's 8, that's 78. Okay, guys, I'm really sorry. That should be 102. Oh my gosh. All right, let me fix this up right here. So 102 is my degree for C. Sorry. Whew, this has been a long lesson. No excuses. But, making some careless mistakes. We all know how easy that is. All right, so I am going to then erase, let's see, I got the signs of, there's 102, that's better, and 102. Yikes, Miss McDaniel. Okay, sorry about that. All right, so we are back on track now, and all of those are right. B is 52, C is 102, and side C is 11.2. Okay. So for triangle number 2, now what we need to think about is that angle, or that 5, the side of 5 swinging in the other way. So we still have 26 degrees. We still have 9, but now my 5 is swung in this way. And so here's A and B and C, and this is triangle number 2. So what we did have was we had that side out here originally at 5, okay? And then we found this angle, if you can see that, to be 50. So 52 degrees, this also has to be 52 degrees. So then this is going to be 180 minus 52, and that will be 128. 180 minus 52, 128. Okay, so that's my new angle B. To find angle C, I'm going to take 180 degrees and subtract 128 plus 26, and oddly enough, I get angle C to be 26 degrees. All right, so if angle C is 26 degrees, now I can use the law of sines and find that third side C. I can take the sine of 26 over 5, and then I also have the sine of C is 26 again over C, so that means that C must be 5. So there's triangle number 2. Okay, so that's another ambiguous case. Lots of work there, pretty tedious. Really sorry about the mix-up with the angle. I was reading the wrong one, so I apologize for that. But hopefully we're back on track with that, and that did not confuse you too badly. All right, so the last one that we have here, it says that downtown is located due north of a straight segment of train track oriented in an east-west direction, according to this drawing. A passenger on a train traveling west to east notes that downtown is visible at an angle of 41 to the left of the track, and after traveling 8 kilometers, the passenger notes that the angle is now 47 and a half. So estimate the vertical distance from the track to downtown. So if downtown is due north, downtown is right there at the top of the triangle. Here's the track. Now it runs all this way, east and west. So if they want to know how far north the town is from the train track, we need to find that value x. And if it's due north, we know that that is a right angle. Okay, so what we have is there's a couple of ways to do this. You can look at the right triangles here and realize we're going to use right triangle trig in the end to get what we want. We've got that big right triangle. Or you can see that we have this littler right triangle to get x. So however you want to do it, it doesn't make a difference. You'll get the same value. But first we need to get some angles in this other triangle. So we're going to start out with this one. We know that 180 minus 47.5, that's going to give us an angle of 132.5. And so then to get this smaller angle up here, we would have 180 minus the sum of 132.5 plus 41, and that's going to equal 6.5 degrees right in here. So I needed that angle because that's the only side that I have of 8. So I have the sine of 6.5 degrees over 8 is going to give me, now what I want is this angle, this side right here, because this can be a side in the little right triangle, or you could go for the big right triangle, either one. But I'm actually going to stick to this y value, and I'm going to use the sine of 41. Oops, hold on. So this will be the sine of 41 over y. So y times the sine of 6.5 equals 8 times the sine of 41. So y is 8 times the sine of 41 over the sine of 6.5 degrees. So as I do that, I get y to be, I'm going to be careful where I look here now, all these numbers running around, 46.4 kilometers. Okay, so now that y, I'm going to replace that with 46.4. Now I'm going to use the smaller right triangle. I have the angle of 47.5. I need the opposite side, and I have the hypotenuse. So I can say that the sine of 47.5 degrees is equal to x over 46.4. So when I cross multiply, I get 46.4 times the sine of 47.5 degrees equal to x. And so that distance is, when we round to the nearest kilometer, will be 34 kilometers. Okay, so this takes us through 4-7, a lot of information. So if you have any questions, it might be a good idea to go back and watch some of these again, try to pause it, and do some of these on your own. Make sure, again, that you are okay with using the calculator to type a lot of these things in.